younger material in archaeology, but it's still interesting to have some understanding of how it works. So that's where we're going with today's lecture. So where we're going to start is looking at isotopes. So that's what we're actually looking at, and that's what we're measuring in rocks to work out how old they are. So an isotope is a variant of a particular chemical element that differs in neutron number. So that's the definition for you. And it's taken from two Greek words, isotope. So iso is Greek for equal, and topos means place. So isotope means equal place. And this is because isotopes of an element occupy the same place on the periodic table because they have the same atomic mass. So, for example, we've got a carbon example. So if we have an atom of carbon, we have 6 neutrons, or 6 protons rather, sitting in a carbon, in a molecule of carbon. You've got 6 protons, and then you've got 6 electrons flying around, and that's your atom of carbon. And then in this carbon atom, we'll have neutrons. And so we have, normally you have 6 neutrons. So we've got 6 protons and 6 neutrons, and this would be carbon 12. So it has an atomic mass of 6 and then 6 additional neutrons, which makes it carbon 12. But then we have 2 isotopes of carbon, and these carbon isotopes differ by the number of neutrons. So if you add a neutron, then you'll end up with carbon 13 because you've added an extra particle. So it's still carbon 6, it still has 6 protons, but with an extra neutron it makes it carbon 13 instead of carbon 12. And we also get carbon 14, which has an additional neutron. So that's basically what an isotope is. So they're atoms of a particular element that differ in neutron number. And because they have different neutron numbers, these different isotopes have slightly different characteristics and behave differently, and this is a major aspect of geology, is understanding these different chemical isotopes and how they behave in rocks. And what we're going to use them for today is looking at radioactive isotopes, because some naturally occurring isotopes are radioactive. So, radioactive isotopes are isotopes that undergo radioactive decay. So you begin with a parent isotope, such as uranium or carbon, and this parent isotope decays to form a stable, non-radioactive daughter isotope. And the radioactivity is a natural process, and these isotopes are naturally radioactive and basically naturally unstable. And we will look at this in a bit more detail. But the concept that we use in geology is that if we know the rate of this decay, this radioactive decay in a particular element, and because we know this rate of decay, and if we can then measure, as geologists, if we can measure the amount of the parent isotope and the daughter isotope, we can calculate how long this reaction has been taking place. And if we know the rate and we know how much we start with and how much we produced, we can work out how old that rock is. So that kind of, in a nutshell, is radioactive dating of geological material. And that's kind of our end goal. So just to look a little bit at radioactivity. So this is the process by which a nucleus of an unstable atom loses energy by emitting radiation. So it's a naturally occurring process, and some elements have nucleuses which are unstable, and they release energy, and there's 3 different types of decay. They release energy and eventually reach a stable state, which is kind of what they are, they're after. So it's nuclear transmutation, where you're actually changing the nucleus of your element. It's a stochastic or random process, so that's kind of how it works. And there's 29 natural radioactive elements on the periodic table. We've become very good at synthesizing them, so there's over 650 man-made ones. But in nature, we have 29 naturally radioactive elements. And as I said, there's 3 types of decay depending on what's being lost from the atom. So basically, you have a radioactive particle, it emits energy and radiation, and you get another particle.
Why do we make radioactive elements?
Yeah, that's a really good question as to why. I guess it was all part of the Cold War, basically, between the US and Russia, that scientists realized after they made a nuclear bomb, because that was synthetic uranium that they used for that, that it is possible by bombarding elements with extra energy, you can actually get them to become radioactive. So I guess it was because we realized we could do it that people were like, well, how much can we do it? And there was a bit of an arms race between the US and Russia in trying to make radioactive material. We do use it for various things, like in the laboratory I work, we use a synthetic radioactive material as a tracer. So we put known amounts in our samples. So when we measure them, we know how much radioactivity they should have. And I know it's used a lot in biomedical sciences, even in chemotherapy and stuff. So, but exactly why is a good question. So, one of the major, so we've got 3 different types of radioactivity. We have alpha decay, beta decay, and gamma decay. And this just is depending on what's been emitted. So in an alpha decay, your parent isotope that's radioactive is losing an alpha particle, which is basically a helium nucleus. So that's 2 protons and 2 neutrons is being lost by each radioactive decay. And so you will change your mass number by 4. So for example, if you had uranium-238 and you have an alpha decay, you lose a helium nucleus and you'll produce 234 thorium. So you've reduced it by 4 mass numbers. And this is the kind of major form of radiation we're going to look at for uranium lead dating. The actual really technical details of this aren't that important to you. It was just so that you guys have an overview of these processes. And then the other major process is beta decay, where you emit an electron. So then you change from a proton to a neutron. And finally, gamma decay, where you just emit gamma rays. So these are the 3 types of radiation. So in order to use this radioactive decay as a dating method, it's very important that we have some understanding of the rate of this decay, because that's what we have to understand to be able to solve for time and work out our old materials. So the rate of decay of radioactive isotopes is proportional to the amount of the isotope present. And so this rate of decay is defined as the number of atoms that decay in a given time and proportional to the original number present. And this is known as the half-life. So if we look at this plot, so this is just a plot showing what I've just been talking about. So the half-life is the time taken for half that amount of isotope to decay radioactively. So this on this y-axis we have the proportion of the atoms length. So we're starting at 1. So that's where you've got everything, your starting volume of atoms. And this is our time on the x-axis in half-lives. So by the time we've, at 1 half-life, we've radioactively decayed half of the atoms present. So it's the amount of time that it takes for a given amount of atoms for half of those to decay is 1 half-life. And so then by 2 half-lives, it's the amount of time it takes to decay that half. So then you've got a quarter of the original material. So a half-life is a measure of how fast radioactive material decays. And what you're actually looking at is the time it takes for half of that volume to decay away. So it's not an easy concept, and I have another cartoon to show you. So this is in a geological setting where you've got a parent isotope. So the parent isotope is the one that's decaying, and the emitting particles and the new particles that are formed are called daughter isotopes. So we have a lovely mother isotope, a parent isotope, and after 1 half-life, half of the mom has decayed away. So you can see only half of her, and she's got a little daughter isotope. And then in the second half-life, half of the half has decayed away, so there's only a quarter of the mom left, and the daughter isotope has grown because a whole lot more daughter isotope is accumulated. And then by the third half-life, we've got only an eighth left, because that's half of a quarter, and the daughter's got much bigger. So the way we use this in geology is that at the origin of the rock, when that rock forms, we only have the parent isotope. And then over time, over various half-lives, till the present time, till we measure that rock, then we have more of the daughter isotope, and we can still measure that little bit of the parent isotope that's left. And by measuring the amount of the parent and the amount of daughter, and we know the decay rate, we can work out the amount of time that's lapsed. Yes?
And does the process of decaying also at some point?
So that's an amazing question. That's really good. So it's sometimes. It depends on the elements. So in the uranium decay series, some of the isotopes then continue to decay as well, which makes our lives very complicated. Because then you can imagine this daughter is having her own kids, basically. But in most systems, no. What you want is that you have a stable daughter isotope so that it stays there. But sometimes there is variation. Yes?
How do you determine how much the original parent isotope was?
Yeah, so that's also a really good question. So what we do as geologists is that we're only looking at this time because we only have the rocks today. So we can only measure the small amount of the parent that's left. But because we know the decay rate, we can back calculate how much there must have been to start with. And these conditions here, like the conditions under which the rock falls, that's also important. And what you're hoping is that there's only the parent isotope and that there's nothing contaminating. But again, in a natural system, it's not always. All right. So is everyone with me? So we're just looking at, a parent isotope that decays and forms a daughter, and our understanding of the rate of that is based on the half-life. So this is kind of going on to the questions you guys were asking, the requirements for an isotope dating system. We need to have a closed system. So we need to have a rock or a mineral inside a rock that is a closed system and that basically locks in these isotopes that we're interested in. So the parent and the daughter isotope are locked in and can't escape. And because we don't want to be losing parent isotope, we don't want to be losing daughter isotope, and we don't want new isotopes to be coming in. So we need a closed system. And we need a constant decay rate. We need to have isotopes which we have a good understanding of the decay rate, and this is consistent. And then ideally, you need to know the initial concentration of the daughter isotope. So what you really want is to only have the parent isotope and have no daughter present. And if there is some of that daughter isotope present, we need to know what that concentration is. There are ways of working around this, but those are our ideal initial conditions. So here are some geologically useful decay schemes. So these are based on various different elements. So we have uranium, and we have two uranium decay schemes. So we have 238 uranium and 235 uranium, both of which are radioactive. And their final daughter isotope in both cases is lead, 206 lead and 207 lead. And so we can use this as the uranium lead dating scheme. And this half-life is a measure of how long it takes for half a given amount of uranium, or the given amount of uranium to decay. And it's incredibly long. It's 4.5 million years. No, 4.5 billion years. I'm not good with my maths. So that's a really long time. So that means that this is a very powerful method for dating incredibly old material, and it's how we know the age of the Earth. Then the next one is potassium. So potassium decays to argon. So the potassium-argon dating method is particularly powerful for dating volcanic material, volcanic ashes. There's rubidium, which decays to strontium, which is also very useful for dating ocean sediments. And then radioactive carbon-14 decays to nitrogen, and is a younger dating method, has a much shorter half-life, but is very useful for archaeology. Yes?
Is that a mistake, the 47 billion years?
For the rubidium, yes, it looks like it, hey? I think it's a typo, but thanks for picking that up. I'll have to check what it's supposed to be. It's most likely a 6, I guess. Or even, no, it's, I'll make a note of that and fix it. Okay, so these are our geological decay schemes that we can use, and but in order to actually date rocks, we need to be able to measure these isotopes in the rocks. So to do that, we use a technique called mass spectrometry. Basically, these are amazing, big, sophisticated machines in which we can measure the amounts, or we can measure the type and amount of elements and isotopes. So this is a schematic of a mass spectrometer, and the big, powerful ones are multi-collector, inductively coupled plasma mass spectrometers, and we can measure the ratios and concentrations of isotopes. So basically, what you have, the main components of a mass spectrometer is a magnet. And you have a source, and you introduce your sample. So we take the rocks into the lab and we crush them down and dissolve them in acid. And they get introduced into a source, which is an incredibly hot ionizing source. So we have liquid, rocks dissolved in acid, and we vaporize them, and this vapor gets introduced into a source where it becomes ionized. So we then have a beam of ions, which is then being fed into our machine. And we have a series of lenses, which helps focus this beam to make it a really nice, narrow, focused beam. And then this beam gets sent through into a magnet. And then in this magnetic field, the different isotopes in this ionized beam are split according to their mass. So that's what a mass spectrometer does. It splits a beam of ions according to mass, and so you get a spectrum of masses. So you go from a single beam to a number of beams. And what happens here is that for example, if you're looking at carbon, for example, we've got carbon 14, carbon 13, and carbon 12. And imagine that these isotopes are like athletes. So we've got the smallest, the lightest one is carbon 12, which is the small, light little guy who's going to run around the smallest part of an athletics field. And the heavier carbon isotopes get thrown out into the field and take a longer path around. And this basically splits our beam according to mass. And so we have a single beam going in, and then coming out, we have 3 beams, and we have a series of collectors, which then collect the different isotopes. So we can work out how many of each isotope we have contained in this rock. And our collectors then all feed through into a detector, which eventually goes through into a computer and actually counts the number of isotopes of your element. So we're able to measure, we split our beam into a spectrum of masses. That's what a mass spectrometer does. So this is the underlying technique for measuring isotopes. Yes?
Doesn't the acid act as an impurity?
Yes. So we have to use ultra-pure acid. We distill the acid 3 times, and we go to a lot of trouble to make sure we've extracted all the impurities out of the acid. But yes, and we're aware of this, and we have various, that's why we have to focus the beam very carefully, and we have various ways of extracting the kind of interference from the acid, but we try and use the cleanest acid as possible so that we know what's going in. All right, so if we look at the 238 decay series, so this is based on uranium-238, which is a naturally occurring radioactive element, and it has a long, quite complicated decay chain. So this is a picture of all of the various decays in the uranium-238 decay series, and it has 14 decays in the chain, and eventually ends in stable 206 lead. So there's various different processes here. There's alpha radiation, there's beta radiation, and all these various daughter isotopes. So that was the question in the front about some of the daughter isotopes themselves are radioactive. And in this case, there's 14 steps before we get to the final daughter isotope of lead that is stable. So the half-life is very long, it's 4.5 billion years, and some of the half-life, that's from uranium to lead, and some of the half-lives for these intermediate daughter isotopes are very short, just a couple of milliseconds. So what we can do in geology is we can just look at the uranium to lead, and we don't need to take into account all of these daughter isotopes. And that's where it's very important that we have a closed system. that we're not losing or gaining any of these isotopes. Another picture which hasn't come out very well. And this is the same, just another way of looking at this uranium series decay chain. So we start with uranium-238, and it decays to uranium-234, to thorium-230, and eventually down into stable 206 lead. So for our purposes, we're just going to look at the uranium-lead aspect of this decay chain. And so what we need to do is we need to find a mineral in a rock. So the mineral, one of the minerals that's making up a rock, that is a very good track for uranium and lead. So the best mineral to use is zircon. And zircon is a zirconium silicate, ZrSiO4. And this is they're small, resistant minerals. They're very common constituents in rocks. And in the actual crystal lattice of the zirconium, uranium substitutes in for small amounts of the zirconium. So at the time that the zircons form and crystallize, we have small amounts of uranium trapped in the crystals. And at the time that these crystals form, there's no lead in them. So we have this ideal initial setup, that we have small amounts of uranium locked into these crystals. And this uranium locked in the crystals basically then begins to decay, and the lead accumulates in the crystal. And we know that all the lead that's accumulating in the zirconium crystals is from the uranium decay. So you basically have a uranium-lead clock ticking as soon as these crystals form. And zircons are abundant. We find them in all types of igneous and metamorphic rocks, and they're small. There's a picture here. So that's 200 microns. They're small, resistant minerals, and they survive very well in rocks and act as a closed system, basically locking in the uranium and the daughter lead. Yes?
So since the system is closed, where do the extra protons and neutrons go?
They basically, you do get the, particularly the gamma, the radiation that's being emitted, the energy that's being released, does release out of the rocks. And that's why, this is why the core of the Earth is hot. It's because of this radiation and the energy that's being released. But the actual, the lead atoms stay in, but the energy is released out. So, this is repeating what I was just saying. So the advantages of using zircon is that zircon is a hard, chemically resistant mineral with a poor cleavage. So that means that it doesn't break open very easily. It's dense and relatively easy to separate out from rocks. So we can collect rocks in the field, we can crush them, and we can actually pick out the little zircons. So they're often zoned, so you can actually look at the history of the grains if they've been melted and cooled repeatedly. And uranium actually has two isotopes. We've looked at the 238 uranium, but there's also 235 uranium, which decays to 207 lead. So locked into these zircons, we have two clocks. We have a 238 clock and a 235 clock. And if we measure both of those, we actually have two ways to get ages and see if they agree. So here are some cathode luminescence images, some kind of X-ray images of zircon grains. And you can see that they have layers where you have an outer rim and various layers normally through to a core of the grain. And these white rings are where geologists have used an iron beam just to ablate off a very small amount of this and to measure the uranium and the lead in this small beam. And what you can do is you can date the core and then the various rims of these grains and work out each time the zircon has been heated and cooled down and the uranium lead clock has been ticking away. So if we look at the oldest geological ages, the age of the Earth is being calculated to around 4.6 billion years. And the oldest rocks that we found on Earth are around 4 billion, and these are from the Acasta gneiss in Canada. And so we have these, they're called gneisses, which are very metamorphosed granites, which there's few kind of spots in the world where we have the very oldest ones. So there's some in Canada. The other place we have incredibly old rocks is also in Australia. So this working out how old the Earth was, and yes.
Like how do we know that the Earth is 4.8 billion years old, while the stone is only 4 billion years old?
Because we believe that the Earth began to accrete and the actual planet formed prior to there being rocks that we can date, and that it took. Yeah, but it's a good question of how we actually know of that difference.
Also, like, what if we find like 8 billion years old stone on the side of a rock, on the side of the wall, and then does that change the history of how we think?
That would, if you found rocks that were 8 billion years old, that would change everything. But we haven't, and our whole understanding of the formation of Earth is that it was around 4.6 billion years, and we only find rocks that have been, because it took time for the planet to kind of cool and accrete and rocks to begin to form, and that the oldest zircons we found are a little bit younger at 4 billion. So, yes.
What about rocks from the outside Earth?
Yes, meteorites. Yes, there are meteorites that are older, and this guy, Claire Patterson, in the 1950s, used rocks and meteorites to try to calculate the age of the Earth. And he worked out that I think the meteorites were a little bit older, and they're from a time when the planets were beginning to accrete, and he was using that to calculate the age of the Earth. So yeah, he was an amazing man in the 1950s. So this is prior to the incredible mass spectrometry technology that we have today. And using quite simple laboratory methods, he measured the amount of uranium and lead in rocks and meteorites in the zircons. He extracted them and measured them, and did some very basic calculations which kind of underpins the kind of modern geology to work out the age of the Earth. And he was also the first person, because he had a very deep understanding of lead chemistry, who suggested that lead fumes in petrol would be bad, because people hadn't really kind of clicked that this wasn't a good thing. So he had a major contribution to make. So this is an example of some of the oldest, I know I was just saying there were 4 billion years, but then in 2000, and then again in 2012, some scientists are always arguing with each other to find the very oldest rocks. And these ones are from Australia, and yeah, they're a little bit older than the Canadian ones, at 4.4 billion years. And so this was using an ion microprobe, which is a very sensitive machine. And this is just a picture, cathode-luminescence image again, of the zircon. And you can see there's an older rim and then this outer material. And they were able to date the very old rims of these zircons to 4.4 billion years.
No, I'm just wondering, when we answer the question in the test, which rock is the oldest?
It's the oldest. I think we better go with that. It's 4.4 billion. That's the latest. So, I guess as geologists, it's all very well to date these old rocks, but geologists always want to know why, and where these old rocks and why we get them. So they, on the various continents that we have, that's where we found all of these old rocks. The rocks that today make up the ocean floor are much younger. So the oldest remnants of Earth are all present on continents today. And these continents are made and formed and deformed and moved around by the process of plate tectonics. And the material gets recycled. But the central parts of the continents today are known as shields or cratons. And they are the oldest bits which have kind of escaped this recycling. And they generally are composed of what's called a basement complex, which is a series of metamorphic and igneous rocks. When we come to the geology of South Africa later in this week, we're going to talk a lot about cratons and these ancient basement complexes that make up the oldest rocks on Earth. So this is just a map of the world showing very generally the age of all the rocks in the world, and this is all based on uranium lead dating. So this orange color is Mesozoic and Cenozoic rocks, and as you know from the geological timescale, that's the most recent part of time. Then looking at the Paleozoic is in green, then Proterozoic is are both blue, or all the kind of shades of blue is the Proterozoic. And then the Archean is the most ancient rocks that we have represented, which is this dark purple color. And I know it's not that easy to see, but there's patches of purple here in Australia, in southern Africa, so Joburg is sitting here, and up in Canada in the Canadian Shield, and various patches up in Russia and North Asia. And these are these remnants of very old crust that have escaped plate tectonics and are kind of in the center of the continents and make up these basement complexes. And the South African craton will come back and talk about more. Yes?
Is it a coincidence that youngest rocks are associated with the Ring of Fire?
No, it's not coincidence at all. That's the basically all of these continental margins. So this ring of fire here, which is the edge of the Pacific plate, the Pacific Rim, and that's where the crust is literally pulling apart and new rocks are being formed. So yes, that's where the youngest rocks would be. If we continue this map out onto the ocean floor and look like the mid-ocean ridge, which runs down here, the mid-Atlantic ridge, there's rocks being formed there all the time. So they basically have a zero age. So yes, if you continued this kind of rainbow pattern, we would have the youngest rocks, the mid-Atlantic ridge, and here around the Ring of Fire on the edges of the tectonic plates. Okay, so then looking at a different element and a different time scale for dating, we're going to have a look at carbon dating. So carbon dating is based on the radioactive decay of carbon-14, and this is used to date organic material. So plants, plant material, animal material, and it's a technique used more in archaeology than geology because it's based on organic material. Willard Libby kind of realized that we could use carbon-14 to date material in the 1940s, and in the 1960s when he published the method and was able to show some examples, he won a Nobel Prize for it. So the isotopes, as I mentioned, are measured in a mass spectrometer. We have to use an accelerated mass spectrometer, these really powerful big ones, to actually see the elements of carbon-14 because it's very rare. And the half-life is around 570,000 years. So this is a massively shorter half-life. And this means that by around 50,000 years ago, all of the carbon-14 in a material has decayed away. With such a short half-life, by 500,000 years, there's no more detectable carbon-14 left. So we can no longer use carbon-14. So we're looking at a very different timescale. We can only use radiocarbon dating to measure much younger material, so it's widely used in archaeology, and we can also only date organic material. So the process, how we form carbon-14 and kind of how it works, is that in the upper atmosphere we have elements, we have nitrogen-14, which gets bombarded by cosmogenic radiation and captures a neutron and basically becomes carbon-14. So we have this carbon-14 synthesized in the upper parts of the atmosphere. And then on land, this carbon-14 gets used by plants in photosynthesis and basically enters the organic pathways. So it gets used in plants and kind of locked into plants. Animals eat the plants, we eat the animals. So you have a whole kind of trophic cycle of animals and plants, and all living beings have carbon-14 in us. And while we're alive, this carbon-14 is permanently replenished. So everybody, all living organisms on Earth have pretty much the same amount of carbon-14. The ratio of carbon-14 to carbon-12 in us is pretty much the same. But once you die and you get buried and become a fossil, or at least get preserved, the amount of carbon-14 in you is no longer constantly replenished. So the carbon-14 begins to decay back down to carbon-12. And so it's this cut off, so from the time of death basically, and when material is buried, that the carbon-14 begins to decay away and it goes back to nitrogen, and we can then use this to work out how old, if we find archaeological material, organic material, we can measure the amount of carbon-14 that's left and work out how old it is. So the organic material that we're talking about, basically you can date bones, skin, plants, wood. And these are just some pictures of some wood that was found in an archaeological excavation. Things like animal hide or leather, basketware, animal bones. So all this kind of material we can extract the carbon and measure the amount of carbon-14. So one example, just because there's millions of examples, basically all of archaeology is dated with, or the bulk of archaeology relies on this dating technique. But one example, and the picture hasn't come out very well, it was Ötzi, the Iceman, who was found in a glacier in the Austrian Alps, and as the glacier melted, a body basically tumbled out of the glacier. And some hikers found this body and called the police, was their first reaction, because the body looked so incredibly fresh. But by using carbon dating, it was dated to 3,300 years BC, so thousands of years old. And this was this amazingly well-formed natural mummy, which had been frozen in the ice for all of this time. It was the oldest mummy in Europe, and there's various theories as to how Ötzi died, and quite an amazing story. And it's kind of out of interest, the body was heavily tattooed and had over 60 tattoos, and at over 3,000 years old, these are the oldest examples of tattoos that were ever found. So that's just, for your general interest, an example of carbon dating. Alright, so to sum up what we've looked at today, we've kind of had a whistle-stop tour of absolute dating. We looked at isotopes, and basically what are isotopes? These elements or atoms of an element with extra neutrons that gives them different properties. We have radioactive isotopes, and this natural radioactivity is the process behind absolute dating. So we looked at the types and mechanisms of decay, and mass spectrometry is how we measure these various isotopes. And then we looked at two examples, uranium-lead dating, using the uranium decay scheme to stable lead, and how we can use this method to date zircon grains, which are ideal clocks basically, as they act as closed systems and lock in the uranium and the lead. And through this we can date the age of the Earth, and we can date the oldest parts of the crust, and these ancient cratons will become important as we start to look at the geology of South Africa. And then a method used extensively in archaeology, carbon dating, and it's also something which people in general have some understanding of. Everyone's heard of carbon dating, which is based on using carbon-14. So that's actually all I have for you today, so we finished a little bit early. But does anyone have any questions? I had an email about putting lectures on Rula, and that the recording on Friday hadn't worked. So all the notes, including today's lecture, are now up on Rula, and I'll have to contact ITS to see what happened with the recording on Friday. It's kind of beyond my direct control. It's here.